Saga sir, shall we start?
Yes, sir.
Sir, we shall start, sir.
Okay, sir. Hello all. Good afternoon. Welcome back to the day two of our workshop. Let's have a very quick review of what we have discussed yesterday, and then we get move on from there. So yesterday we discussed about building a decision tree. How does the decision tree algorithm work? In this example, we used cart as our decision tree algorithm. So we discussed about what happens inside the cart algorithm and how we use the decision tree for our decision making. And by the end of the session, we also briefly talked about how to build the decision tree model using Python. We have seen some example on how we did the decision tree model, how we built the decision tree model in Python. And there were a couple of questions regarding how do we improve the model performance? What are the other things that we can do with the decision tree? So today we will first start with how do we improve the model performance, and then we move on to our next topic. Let's see if there are any questions. Just a minute. Okay. Now, let's start with some of the advantages and disadvantages of tree-based algorithm. When I talk about tree, right now we are only discussing about cart, the single decision tree. The basic advantage of a decision tree is it's so easy to explain, it's so easy to interpret. You remember how we explained the decisions that we have to make using the decision tree yesterday? There are like 3 decisions. These are simple nested if-else rules. So if we have to make a decision, we just go through this decision tree, and in one of these nodes, our data point will end up, and based on the node that the data point will end up, we will make our prediction. So that's why it's so easy to explain. Even someone who is not aware of machine learning, a business stakeholder or a business leader doesn't have to know how these 3 algorithms work behind the scenes in order to understand how to use this decision tree in the decision making. That's the biggest advantage when we go with a tree-based model. Variable selection and handling missing values. This is another very important concept in data science. Like I said, before you even begin the journey of learning data science, we have to learn a lot of pre-concepts like data management. To some extent, we should also learn about statistics. We should also learn about the variable selection, handling missing values. So these are all part of what we call as the feature engineering part of the data science. Maybe in future, one of the sessions we can exclusively concentrate on feature engineering part of the data science. But for now, just to give you a highlights of what this variable selection and handling missing values means. We can have n number of variables to start with. When we begin a data science project, we collect large volumes of data, that's in terms of observation and also in terms of variables. But not all the variables that we collect would end up in the model. When we say model, the decision tree. Look at this decision tree. When you actually look at the data, there are like 3 variables: student, balance, income. So these are the 3 variables that are given as input to the cart algorithm. But when you actually look at the decision tree, it has used balance twice, and income. So there is no where in the decision tree a variable called student is being used. Though we gave this as an input to the cart algorithm, why did the cart algorithm not choose this particular variable student anywhere in the decision tree? The reason is tree go by the principle of binary partition, and the criteria to decide if the partition is good or not is, in this case, we used Gini index, right? Either we can go with entropy or we can go with the Gini index. So in this case, we went with the Gini index. So anywhere during this construction process of the tree, this variable student was not able to provide that improvement in the Gini index, or decrease in the Gini index. When I say improvement, it should decrease. Compared to the parent node, the child node should have less Gini index. That means the node has to be more pure compared to its parent node, right? So nowhere in this decision tree process, this variable called student was actually able to give you that improvement, able to decrease the Gini index. And that's why this variable student is not part of this decision tree at all. That is what when we mean variable selection. In place of this decision tree algorithm, if we had chosen some other algorithm like logistic regression, another very popular algorithm for classification, one of the heavily used algorithms for classification. So instead of using the decision tree, if I had preferred to use logistic regression, then variable selection is a manual process. As a developer of that model, we have to decide what variables should go as input to the model. If we, let's say, give 10 variables as input to the model, like how we give here, like we gave 3 input variables to the cart. In place of cart, if we use logistic regression, it would end up using all the 3. It will not be able to select the variables that is having some impact on the target variable. Instead, you gave me these 3 variables, I'm going to use these 3 variables as part of the model. When that happens, the disadvantage is there could be some variables which has no impact on the target that we are trying to predict, but still it becomes part of the model. It might lead to some sort of overfitting. It might sometimes even lead to confusing the model as a output, right? So one of the biggest advantages of going with a tree-based model is they are capable of handling the variable selection themselves. You can give hundreds of variables to a cart algorithm, and it will decide what variables to be part of the model finally, which variables will not be part of the model. Okay, so that's another very good significant advantage that we get from the decision tree based model. Handles missing values. So missing value is something like this. Let's say for this observation number 4, we do not have this information. Balance information is not there. It's like null in your database concept, right? So there is no value. There is no value in that particular field called balance for this observation number 4. Now, when such thing happens, you have to impute them before you actually pass the data to any algorithm, not for cart, for rest of the algorithms. Maybe not for all of them, but for some of those algorithms, right? So that's another advantage going with cart algorithm. Even if you don't impute, that's fine. It would use the information that's available in rest of the variables to make a decision. Doesn't have to solely depend on this missing value imputation in order to learn for that particular observation over here. So that's another second advantage. It handles the missing values on its own. Like we have advantages, of course, there will be some disadvantage. For each algorithm, that's going to be the case. There will be some advantage, there will be some disadvantage. So the disadvantage is the tree-based algorithm is they are more prone to a problem called as like overfitting. Now, what is this overfitting? Overfitting is a concept where your model learns something more that's not necessary in order to make the right prediction. If you look at the data, the input training data that we are trying to pass to the cart model, and the cart model is learning these rules, and these rules are in order making those predictions. Now, just for the sake of argument, let's say we have one more variable in this data. I'm just going to pictorially represent it. I'm not going to create the data and pass this to the cart model again. Just for the sake of argument, let's say we have one more variable that is going to be part of this data, gender, male, female. We create this variable, right? Now, accidentally, in this data set, I am going to create something like this. Wherever gender is male, most of the times, let's say default is no or yes, both are there. But wherever gender is female, we just say default is no. So it's like creating a variable that has some impact on the default status. Ideally speaking, when you talk about customers, whether a customer is a woman or a man should not have any impact on their default status. Default in this case means someone who took a loan and they are paying back this loan to the bank, and if they don't pay, that's called as default, right? So now gender would really not have much impact on this. Gender has nothing to do with if the loan taker is going to pay that amount healthily back to the bank, right? Either it's male or female, if they are having some economic problems, they would default on the loan payments. That's generally what happens when we look at this type of credit related data. But in this training data set, we accidentally, I'm stressing this word, accidentally, right? We accidentally created this gender column, or we accidentally took the data in which this gender column behaves in a different way. Most females did not default, so default is no for most females, and default is yes or no, both for males. Now, when you pass such data to this cart algorithm, what happens is when it is trying to learn, remember how it actually works. First, let's say we have now x1, x2, x3, x4, and y. So these are our 4 variables. Now, x4 is this new variable which I included as gender. Now, to start with, this is our root node. At the root node, let's say we have 60-40 split. And we are trying to split this using one variable. Let's say that was x1, balance less than 1800. So that was the root node split in our previous iteration. Now, because we have gender, and gender, male, both yes or no are there, gender female, no defaults. So in this place, instead of this balance, gender would take the first level split, because gender is the one that is going to provide that maximum decrease in Gini. Let's say here the Gini to start with was 0.4. Just a minute, sorry. So here the Gini was 0.4, and at the root node split at the child level, let's say it is decreasing to 0.8. Now gender is equal to female. Let's say this is the split criteria that we are going to use. And this is the split criteria that has produced the maximum decrease in Gini. Now, the whole tree has got changed because of this newly created variable gender. But if you just practically think, gender should not have any impact on a person defaulting or paying the loan healthily. Accidentally in our data set, it was represented like this. And when the model is trying to learn, it doesn't really think if this pattern is very common or not. It simply look at the data and try to learn which variable is giving me this maximum decrease in Gini, and I'm going to use that variable to split it. So what happens if we go with this type of tree now? Wherever gender is female, we will be predicting that they are not going to default. But in future, that's not going to be the case. That was an accidental pattern in our data set, but that's not the true pattern that's prevalent in the business. Now, every female, we are predicting that they are not going to default, but in reality, there are some females who are defaulting. So where did we go wrong? We did go wrong in overfitting. Overfitting is a problem when you have some unwanted pattern, that is available in your data set, and you learn for that particular pattern, which is not the real pattern in the business, that's simply we term as overfitting. And as the tree keeps growing, as we keep growing, adding more and more decision layers to it, at some point in time, there could be a possibility that, hey, at this particular part, trees are actually overfitting. So to avoid such overfitting, we have a solution. The solution is called as pruning. We can prune the tree. So we can grow the tree and we can start cutting out some of the branches if we think that the tree is actually overfitting. Now, how do we prune this tree? That's the next question, right? So pruning the tree can be done in multiple ways, but the most method for pruning is controlling the tree by restricting the tree growth to a particular depth. So there is an option called as maximum depth. So if you just allow the tree to grow, it will just keep growing all the way up to, let's say, 10 levels, 12 levels, or even 15 levels. But if you restrict the tree from maximum to a maximum depth, let's say we say maximum depth is equal to 10. That means we would allow the tree to grow a depth of 10, and we are forcefully stopping. This is called as early stopping criteria. So yesterday we talked about the trees will continue to grow as long as there is information gain or there is perfect split, there is a perfect node. But if we add an early stopping criteria, now the condition is if the early stopping criteria is not met, then continue to grow. If it has reached a place where the node is perfect, no more split. If there is no decrease in Gini, no more split. But even before that, if the early stopping criteria is reached, like if it's a max depth is equal to 10, it has reached a depth of 10, but there is still possibility to grow the tree because there is still possibility to decrease Gini, but it is not allowed because we are giving this early stopping criteria that's like max depth is equal to 10. Now, how do we know if we are overfitting? So to know if we are actually overfitting, we actually compare the performance on training and we compare the performance on test. Overfitting is when the model performs amazingly good on train. Let's say on my training, my accuracy is 0.95. And on test, my accuracy is just like 0.7. Look at the difference between the training accuracy and the test accuracy. Training accuracy all the way up to 0.95, testing accuracy 0.7. So that's an indication that we have overtrained the models on the training data so that it is doing amazing job on training, but not so good on test. So to give you an analogy, think of this. You have an exam and you are preparing for an exam. How do you generally prepare for an exam? You prepare for an exam from your textbook. So you have a textbook for that particular subject. You read and learn from the textbook. So the textbook is the training data here. The model is trying to read and learn something from the training data. Then to judge how good your learning is, then you have to take an exam. So your exam is nothing but the test data. Now let's imagine this situation. In the exam, I said the question paper and all the questions that came, that I gave in the question paper directly came from the textbook examples. There are some solved examples in the textbook. I picked those questions and I put those questions in the question paper. Now, if you go and take an exam now, generally speaking, most of the people will do good, will score good on the exam. Why? I picked the same examples that were there in the textbook and actually gave them on the question paper. So most of the people will do good. But if I set a question paper like this, I pick a similar example from the textbook, not with the same numbers, but slightly different numbers, and I give that problem in the text, in the test as a question. Now, do you think everybody would score good? Not everybody. Some of them will struggle. Why they would struggle? This is the simple reason. In the process of learning, some of us would not pay attention to the knowledge that is required to learn. Instead of, we just try to by heart what is there in the textbook. It's like remembering. It's like memorizing things. You just memorized what is there in the textbook, and if the question is same on your question paper, you just dump it. So it's not a test of learning, it's actually a test of your memory, because the solution is exactly same. You just remember that and you try to dump that on your test paper, so you would score naturally good. But if the question is not exactly same, the numbers are slightly different, unless you have learned the logic of how to solve the problem, you would not be able to solve this problem on the question paper, right? So that's a kind of analogy that you can use for training versus test. Questions are as it is from the textbook, you score good. So you have actually overfitted. That means instead of learning for the logic, you have just tried to memorize that. Questions are slightly different than what you see in the textbook, then you are scoring not good. So your test performance is degrading, your test performance is coming down. So that means your logic is not sound. Your memory is good, but not your logic. So similarly here, when we talk about overfitting, we simply think training and testing accuracy should be like more or less very close to each other. If there is a significant difference between training and testing, that means the model is doing good job on training data, but not so good job on the test data. So that's an indication, that's a clear indication that the model is actually overfitting. So when we try to avoid overfitting, we try to prune the data using some criteria. In this case, I'm going to use my criteria as max depth, so that the model doesn't overfit. The model has good accuracy both on training and as well as test. Okay, let's see if there are any questions. Then I will go back and show this example again in Python. How do we do the pruning? How do we increase the model performance if possible? If it is not possible, then I might not be able to, but I'll try if there is a possibility to increase the model performance. Okay, so far so good. Okay, let's get back to the model that we have built. Okay, yesterday we built this model, and when we predict, we we are predicting on the test data set. So this is, let's say, print test accuracy. So whatever the metrics that we are printing here, that's like coming from test data set. Okay, let's rerun this again. Doesn't take much time, a couple of seconds, and we should be done. Okay, let's print saying this is test report. So what we are printing here is the test report, and we will also print the train report. Let me print the train report. For that, we need to have predictions, right? Predictions underscore train. I'm naming it as predictions underscore train. What's the model? Model name is dt dot predict. We are going to pass for predictions now, x underscore train. So you have predictions from train as well now. Now let's print this. Let's call this as train report. Confusion matrix of y underscore train, comma predict underscore train. Look at the accuracy on training data set, perfect one. On training data set, we are able to predict everything so accurately. Let's look at the confusion matrix to understand this a little more in detail. This is actuals, right? No and yes. These are predictions, no and yes. 228100385. That's the confusion matrix that we have got. Whenever we predicted no, all of them were no. We did not make any false prediction at all. Whenever we have predicted yes, all of them are yes. Again, we did not make any false prediction at all. So our accuracy on training is 100%. That's like too good to believe, something that should not actually happen, right? So that means there is a possibility that our model is overfitting. And on test, we have an accuracy of 0.92, and on train, we have an accuracy of 1. So there might be a chance that this model is overfitting. Now let's try to control this overfitting by playing with these parameters. Like you have so many parameters. So we can pick one of them. I'm not going to go with the rest of the parameters. Max depth is enough. Now let's say we go with a max depth of 7. So you would be definitely more curious, why did we start with 7? What was the reason I chose 7? Is it because it's my fancy number? No, that's not true. There is a reason why I started with 7. Now let's see, once we have a good report on testing and training accuracy, you would see, wow. So on the test now, it jumped to 0.959. It's almost like 0.96. And on train also, it's like 0.96. So the training performance decreased a little bit, right? A little bit, some errors here and there. We still have 96% accuracy, That's fantastic to go with. But look at the improvement on the test set. On the improvement of the test set from 0.928 to 0.958, that's like a fantastic improvement. So max depth, when we did not give anything, might have allowed to go, let's say, all the way up to 10. Now let's run with 10 and see what happens. And if we go with all the way up to 10, it decreased. 0.947 is the training accuracy, and the training, sorry, 0.978 is the training accuracy, 0.9475 is the test accuracy. That means there is something wrong happening. So let's stick to 7, where I was actually getting a better result, both on train. My train was 9.959, and similarly the test would be 0.967. That's good, right? So the reason why I actually choose with 7, this is a thumb of rule. This is a rule of thumb, my mistake. We generally take a look at how many input variables are there. See here, how many input variables are there? 17. The common rule is we do not go beyond 50% of it. So 50% of it is like 8 point something. So just somewhere below 50% should be the ideal number that we have to try with. So that's the reason. 8 is something that maximum that we would go with, 8 or 9 in some cases. So I wanted to try with 7, 8, 9. So we will try with 7, 8, 9. So wherever we get the best results, so that's ideally we would try to go with. Or else we can do one thing. We can just put all of this in a loop, changing max depth from, let's say, 5 all the way to 15, and give a comparison between the training report and the test report, and see where you have a good balance between the training report and the test report, and pick the value of maximum depth where you have seen very minimum separation between training and test report, right? So these are some of the widgets, the tools that you have to practice if you have to master yourself as a data scientist, right? Now, anybody can write these like 10 lines of code. It hardly doesn't really matter, not even as difficult as writing probably a simple SAT program in C++. There is no difficulty at all. It's so easy. Now, then why don't we have so many data scientists? Why don't we have so many people who are practicing data scientists? The reason is it's just the beginning of it. And to master it, you need to learn a lot of other concepts. Right now, I introduced a concept called as overfitting, and there is also a concept called as validation. Right now, we are not doing that. But if you have to be really a seasoned data scientist, then we have to talk about what validation is, what type of validation techniques exist, right? So as we bring in more and more concepts, and as we refine the process of building the model, and we make sure by the end of that process, we get a solid model which is stable and giving us good predictions as an output, that's where you become a seasoned data scientist. For that, you need practice. Practice maybe like with multiple use cases, multiple algorithms, by involving all these concepts. Okay, let's pause here. I hope now that's clear. I think there were a couple of questions before. We probably have answered them as well. Like how to know where to split. We discussed about it, how to know where to split. If there is a variable, let's say the variable is a continuous variable, something like height. Height is ranging from let's say, height is ranging from 5.0 to 6.7. That's the range. We have 1,000 observations. N is equal to 1,000. Now we divide them into percentiles, 10th percentile, 20th percentile, all the way up to 90th percentile. If you want to go with fifth percentiles like 5, 10, 15, that's also good. That's fine. So 10th percentile, let's say, is 5.2, 20th percentile is 5.31, 90th percentile is 6.4. So we try these splits. So height less than 5.2, then height less than 5.31, height less than 5.42, height less than 6.4, right? All the way. So these are probably the 10 split points that we would try in this variable. Now within these split points, whichever split points gives us the maximum decrease in the Gini value at the child nodes, that's the best split available in this variable. Now let's say this is the best split available in this variable. Now you go to other variable, find the best split in that variable. You go to other variable, find the best split in that variable. Once you have the best splits in each variable, you compare them across all the variables and pick the best variable that's giving you the maximum decrease in the Gini from the parent node to the child nodes. That's going to be the variable that would split at that particular level. It's always calculated at the parent node. From the parent node to the child node, it's a competition between across all the variables. Whichever variable gives you the maximum decrease in Gini, that's the variable that's going to make the split over there. Okay, so far so good. The decision tree is good enough now. Of course, there are a few more topics, as I said. You would have to master them slowly, one by one. Now let's move on to our next topic. In the next topic, we are going to introduce you the concept of ensembling. Now, what is this ensembling? Why do we need this ensembling? So there is a very famous saying, collectively, we will have more strength and intelligence than just being an individual. And we all can easily believe that, right? So let me start this with an analogy. Tomorrow, we have an exam. And we probably have only one day to prepare for an exam, which is a common situation that we all end up with. No surprises there. Now, within the next 24 hours before the exam, you have to learn how much you can so that you can go and attempt the exam and get the best possible marks for you. Now, to get the best possible marks for you, what is the limitation that you have? The limitation is nothing but your learning capacity. How much your brain can learn in the next 24 hours, that's what is going to reflect in the performance of your exam tomorrow. But imagine a situation where instead of you learning on your own, you have to, or at least you decided to learn as a group, which is not allowed for some reasons, but just for the sake of argument, let's say that's allowed. Now you are a team of 10 members, you and your friends. Now you have 24 hours to learn and you have 10 people. Now what you do, you can collectively learn. Collectively learn in the sense, like you all read through the same material so that you prepare enough. And then next day you go and try to give the exam. But while giving the exam, you don't depend on your own learning. You are going to combine all of your learning. Say, for example, it's all multiple choice questions. And first question, let's say someone reads the first question loud, and all 10 friends together as a group answer this question. Hey, first person says the answer is A. The second person says the answer is B. Third person says again the answer is A. Fourth person says the answer is A, like that, right? Now, out of 10 people, let's say 7 people said that the answer is A, and the remaining few people said the answer is something. Now, this is what we call as the collective intelligence. Now, in a democracy, majority always wins. So you would simply think, okay, since 7 out of 10 people had said that the answer is A. The answer is going to be A. We are going with A. Now, all the 10 people answer the question as A. Don't you think you would be scoring slightly higher marks, if not slightly? I mean, compared to a individual scoring, you should be able to score much, much better with this collective learning, right? So that's exactly what is the concept that we are going to bring in here. But with a little more enhancement. Let's see what that enhancement is. I'll explain that enhancement. Maybe in the same analogy, let's add one more enhancement. The enhancement is, what's the point if you have 10 friends, all the 10 friends are learning from the same book, you still have only 24 hours to learn. Everybody struggle to learn, and you still don't combine, even with all the combined intelligence, you still don't score good marks in your exam. This can happen with anyone, right? Now, what's even a better strategy is to divide the book into few chapters. Let's say there are 20 chapters in the book. Each individual divide 2 chapters. First 2 chapters, person 1. Second 2 chapters, person 2. Third 2 chapters, person 3. And then you learn only these 2 chapters. Now you have 24 hours to learn, but only 2 chapters. So you can literally actually learn everything, because you're not trying to learn from the entire textbook at once. You are just only going to learn 2 chapters at a time in the next 24 hours. So that means your learning capability has to be increased for sure. So you are just learning those 2 chapters. I'm ignoring the fact that there will be interdependency. That means to read chapter 4, you need to also know about chapter 3. There is that interdependency in the textbook, but for the sake of argument, let's say there is no interdependency among the chapters. Each chapter is independent. So you are trying to learn something like that. Now you go to the exam, you try to attempt this exam using collective intelligence. Question number 1, hey, it came from chapter 1. So the chapter 1 person answers it. Question number 2, it came again from the chapter 1, the chapter person answers it. Now you think your learning, your collective intelligence should score much more marks. Why? Because each individual is given a very limited task, which doesn't really overwhelm their learning capacity. So ideally expecting each individual has learned very well, so they should be able to score good marks in the exam. But there is a catch here. That catch is called as the human thinking problem. What is that problem is, let's say 10 friends are there, and one of the friends thinks that, hey, anyway, all the 9 other people are going to read. Why do I have to read? When the question comes from the chapters that I am supposed to read, I'll give some random answer. If all the 9 other people read very well, they are still going to get very good marks. Why do I have to put effort in reading even those 2 chapters, right? Natural tendency. What if all the 10 people thinks like that? Not just only one person, not all the 10 people thinks like that. So there can be worse situations. Like instead of learning individually and trying to attempt the exam individually, if you just simply rely on others, the situation can turn up even bad. So we need to have a balance here. We need to have a check here. To keep that check, what happens? We will not depend only on one individual, but we will actually depend on many individuals. How? Person 1, chapter 1, 2, 3. Person 2, chapter 2, 4, 6. Person 3, 3, 4, and 9. So one chapter is being read by multiple individuals, not just only one. Right? So we are making sure that there is good possibility that one chapter is read at least by 3-4 people. So when the question comes from that chapter, we still ask like, okay, you are the people who read these chapters and you have to answer them. You give your answer. That even 10 members can answer that. And now from that, you pick what is going to be the common answer. This exact concept is called as bagging, right? So that was an analogy on how a collective learning is always better than individual learning. And we are going to replicate that learning here in the form of ensembling. So what ensembling means here is, compared to individual decision tree, which has its own limitations, trying to learn from a large volume of data, which is definitely overwhelming for the tree. It can overfit so many problems, the other problems that we have discussed too. If we can train multiple trees and combine those multiple trees, that's the combined learning of those multiple trees, which is going to be much better for us. That's what we are going to call as bagging. The technical name is called as bootstrap aggregating. It actually came from statistics. In statistics, we have something called as resampling methods. So this concept of bagging came from the statistical concept of resampling methods. In that resampling methods, one of the resampling method is called as bootstrap aggregation. So this concept is derived from that bootstrap aggregation. But in short, in data science, we simply term this as bagging. To understand this resampling methods and sampling techniques, we have to deep dive into the statistics, which is beyond the scope for this discussion. But in short, I'll explain what bagging means with a simple example. Let's say we have a data set. This is our training data. And this data, I can try to learn a decision tree. So it would learn something like this. And at some point in time, it would try to stop. So this is the single decision tree. And this decision tree, let's say, has an accuracy of 0.8, which is not good enough for us. We want this model to be even more accurate. We want to improve the performance of this model. For us, 0.8 accuracy is not at all good, not even satisfactory. So that's where we think about ensembling methods. What we do in ensembling methods is, from this training data, we are going to create multiple training data sets. And we call these training data sets as bags. So this is bag 1, this is bag 2, this is bag 3, this is bag 4, this is bag 5. How are these bags created? So let's say in the training data set, we have 1,000 observations. And in each bag, let's say I am going to take 400 observations, 400 here, 400 here, 400 here, 400, another 400. Wait a minute, we only have 1,000 observations. Where did we get 400, 400, 4, 5, 2,000 observations? We do not have those many, right? So in bagging, we allow something called as repeated sampling or sampling with repetition. What that means is, an observation that goes into bag 1, the same observation can also go into bag 2. So observation sample once can be sampled again. So that way I can create any number, even I can create 500, 500, 500. So an observation can be multiple times a sample. So that's how these bags are created. So each bag, let's say, has 400 observations now, and we are allowing these observations to get repeatedly sampled. So 2,000 observations is also fine. This is the analogy of chapters. So this is the textbook. In textbook, I have 20 chapters. Now, when I try to take a small fraction of my textbook out. I'm trying to take chapters out. So first chapter, second chapter, third chapter goes into bag one. Second chapter, fourth chapter, sixth chapter goes into bag two. So that way the first chapter is present both in bag one as well as bag two. So that's the repetition that we are actually talking about. And that's the reason why I gave that analogy at the beginning of this discussion. Data science is more easier to understand using that layman analogy than simply dumping ourselves into the statistical concepts of sampling, resampling, and then etc. etc. Okay. Now, for each bag or in each bag, we are going to learn a tree. So this is one tree. This is like once we divide them into chapters, each individual, this is person one, each individual trying to learn from their own assigned chapters. Right? So each decision tree is trying to learn from what are the observations that are assigned to them. In a way, each tree would be slightly different from each other. Like they are learning from different examples. So each tree will have its own structure. Some of the trees would be unique. Some of the trees would be like different. Okay, so we would get 5 trees now. So this is the learning process. Now comes the aggregation process. Whenever we have a test data set, we pass the test data set to all the five trees that we have developed. So let's say we give the test observation to all the 5 trees, and each tree gives us a prediction. This is P1, this is P2, this is P3, this is P4, and then P5. We have 5 predictions, right? Now, how do we combine these decisions? Either by voting, which is nothing but the majority, or by aggregating. If it is a regression, then we go by aggregating. So if it is a regression, each prediction is a number. So this is 10, this is 12, this is 1, this is 14, this is 12. So what's the average of this? So that's going to be our final prediction. So aggregation in case of regression, voting or majority in case of classification. So if it is a classification, hey, this gives a prediction as S, this gives a prediction as no, this gives a prediction as S, this gives a prediction as no, this gives a prediction as S. So what's the majority? Majority is S. So our final prediction in this case, majority is going to be S. So our final prediction is also going to be S. So that's the concept of bagging. Individual trees, when it try to learn from large set of observations, struggle to learn, and it will have some limitation. And with that limitation, it is probably able to achieve an accuracy of 0.8, not beyond that. Even if we try to do everything, restricting the trees from overfitting, controlling the tree to a particular depth, everything done, but still the accuracy doesn't shoot up more than 0.8 or 80%. How do we improve the performance? The other alternative is combining these trees using an ensemble technique by using a concept like bagging. So you create multiple sub trees from the larger training data set, and we resample the data from the same training data. We create multiple subsamples, and these subsamples, we call them as bags. So each bag 1, bag 2, bag 3, it depends on you, how many number of trees you want to build. There is no restriction that it has to be 5. You can all the way grow up to 100 as well. So there is no way that you could say only I can build 5, or I can build 20, I can build 25. You can build as many as them. How many number is good is called as a hyperparameter. I will talk more about hyperparameters later. Don't worry about it right now. So we will decide how many number of trees that we are going to build, or how many number of bags we are going to get created like this. But in the end, on each bag, we will try to learn a decision tree. We will try to create a decision tree. And when we want to make decisions out of this, we combine the decisions. We pass the test observation to each tree, and each tree gives us a prediction. And you try to aggregate that prediction by using the voting mechanism, or by aggregating, or by averaging it in case of a regression. Okay, so far so good. Any questions? Okay. Now let's jump to okay, let's leave that. Let's move to the next slide. Anyway, splitting the train and test is generally done with a random split selection. So in yesterday's code, I wrote something like this. I think this question is repeatedly coming, so let me explain briefly. We have something called as train underscore test underscore split. So this is a function that we are using to split the data. And it takes 4 arguments. What are those 4 arguments? X, Y, test underscore size, and random underscore state. Let me write it clearly. Random underscore state. Now, it produces 4 outputs. That is X underscore train, X underscore test, Y underscore train, and Y underscore test. Let me visually show you how this actually works. X is nothing but a kind of matrix, a data frame for you. So X is a large matrix like this. You have rows and then you have columns, X1, X2, X3, so on, all the way up to Xm. I'm assuming there are M variables over here and N observations. So this is a M by N matrix. Y is a vector or a single column. You can think of this as a single column like this. So this is your Y. Test size is equal to, let's say we give test underscore size is equal to 0.2. That means we are asking for a split where 20% of the data go into test and 80% of the data go into train. So that's what we are asking. Test size is equal to 0.2 means. So just visually think of this. This is my X and this is my Y as of now. What I'm asking for is a split like this, where this becomes X underscore train, this becomes X underscore test, this becomes Y underscore train, and this becomes Y underscore test. But it's not like all the first 800 observations. Let's say we start with N is equal to 1000. That means we have a sample of 1000 observations in your X and Y. It doesn't mean that first 800 will go into training and remaining 0.2 will go into test. No, that's not how it is. It will happen with a random selection process. Let's see how that random selection process happens. First, it creates an array of the size N. So 0, 1, 2, 3, all the way up to 999. Why it has to create an array of this? It creates an array because there are only 1000 observations. So it takes the maximum number of observations and creates an array of this. Then using a random number generator, there is a random number generator algorithm that's not specific to Python, but that's specific to your operating system. So using a random number generator algorithm, it will create a range of, let's say, 0 to 800. So it has to, this algorithm has to run for 800 iterations. And out of these 800 iterations, every time, so this is iterations, not numbers, every time it go to this array, pick one number, and put that in the training set. So first time it picks 3, then again it will pick, let's say 9, then again it will go to this array, it will pick 11, something like this. Once a number is picked, that will be eliminated from this array. So once 3 is picked, it is eliminated. Once 9 is picked, it is eliminated. Once 11 is picked, it is eliminated. So this array will keep diminishing, but this loop will run for 800 times. Let's say at the end of 800 iteration, it filled this array with some 800 numbers that it has randomly chosen from this. At the end of the 800th iteration, what happens? Train will have 800 and remaining 200 will remain in this array. So we have some numbers in training and some numbers left, 200 numbers left in this array. So these numbers become our test. Then using these index positions, it will select the training data. Training data should come from row number 3, row number 9, row number 11, row number 16, row number 18. So X underscore train is populated using this index. X underscore test is going to get populated using the remaining index. Same way, Y underscore train is going to get populated from this array, and Y underscore test is going to get populated using the indexes of the remaining things in this array. So that's how this random split will happen. Though we can simply write this code, train underscore test underscore split with these 4 arguments, this is exactly what happens behind the scenes. That's the beauty of Python that I have been talking about since yesterday. So if you have to do this processing manually, first to try to create an array, then use the random number generator algorithm, run it for a loop of 800 times, randomly go pick one number, create this array, take the left out array. You need to know data structure so strongly, otherwise you would not be able to do this, right? But that difficulty is completely eliminated with the help of these functions. That's the beauty of all these inbuilt functions. You do not have to worry about the complexity of the data structures, creating those arrays, populating those arrays and taking them, striking them out. All those things is taken care by this particular function. All you need to know is you need to pass two objects as input. In Python, everything is an object. If you are worrying why I'm using different names, in Python, you just simply name everything as an object. So X is an object. Though it's a 2-dimensional array, Y is an object. It's a 1-dimensional array. So X is one object, Y is another object. So you need to give 2 objects as an input. Test size, you need to tell the ratio of what should be the ratio of your test size. If you say ratio of the test size is 0.25, then it will divide this by that particular number and say, okay, these many should go into test and these many should into train. And that's how once these array indexes are generated, it can select those rows into X train and X test, and similarly Y train and Y test. I hope that's clear now how this random number generator works behind the scenes in creating these four objects for us, 4 data sets for us. Okay, now let's get back to our discussion on the random forest. Okay, now we have already discussed this. This is my data set. I'm trying to divide the data set into multiple bags. So these are my bags, and on each bag, I'm going to train a tree. So this is the tree. This is tree 1. This is similarly tree 2. This is similarly tree 3. This is called bagging. Okay, so far we are only talking about bagging. There is a minute difference between what bagging is and random forest is. We will introduce that difference now. Okay, each tree will give you a result when you have to make a prediction. Each tree will give you a prediction, and you are trying to either do the majority voting or try to do the averaging. Voting in case of classification, averaging in case of regression, and that's how you are going to get final result with one added criteria for random forest. that is called as variable selection, or you also can call this as variable filtering. So what is this variable filtering as an additional concept? Let's say we created this bag, and this bag has 400 observations. Similarly for other bags as well. Let's say this is bag 1, this is for bag 2, this is for bag 3, this is for bag 4, so on, up to, let's say we create 100 bags. So for each bag, we will perform something called as a variable selection, and let's see how this variable selection is going to get performed. Now, what are the input variables here? X1, X2, let's say all the way up to X10. So these are our input variables. To start with, each bag has these 10 input variables. Now, when I am trying to make this split, generally what do? We try to run a competition between X1 to X10. Whichever variable has given us the maximum decrease in Gini, that variable we will use to make this root level split, but not. In random forest, we do slightly differently. What we do is, every time we want to make a split, we will do something called as a variable filtering or a variable selection. We don't run the competition across all the variables. We will run by selecting a sample of them. Let's say X1, X4, X6, X9. So we are going to only select 4 variables at a time. Anytime when we are trying to split, when we are trying to make a split, we don't compare all the 10 variables. At the data set level, we have 10 variables. So here, n is equal to 1000 and m is equal to 10. M is the number of variables we have. But whenever we want to make a split, we don't run the competition across all the 10 variables. We would select some p variables. How many of them? We will decide later. Generally for regression, p is equal to m by 3, and for classification, p is equal to root over m. So if we are performing regression, 10 by 3, 3 point something, so we would select 3 variables at a time. If we are performing classification, again root over 10, 3, we are going to select 3 at a time. Why this additional variable filtering? Why this additional variable selection? This is to bring more democracy into this process. Now, just because these data sets are slightly different, it doesn't mean that the trees that are built using these data sets will be different also. They will be similar. See here, this tree is having same structure. This tree is also having same structure. This tree is also having same structure. What's the problem? The problem is all these trees are learning similarly because they are trying to learn from similar data sets. And that's something we do not want to happen. We want to avoid that. So to avoid that, we threw one more competition there. We compete saying that, hey, when you are trying to split here, try to run the competition between X1, X4, X6. That's it. For this data set, you try to run the competition between X2, X5, X7. So in a way, we are trying to force these trees, hey, you have to learn, there has to be some uniqueness about you. Each tree, you try to build your own unique tree. Don't try to replicate or don't try to copy the other trees. Similarly, we are trying to control this learning of each tree by throwing in additional selection mechanism. In this case, it's going to be a variable selection. So when we use this variable selection on top of bagging, that's what is called as random forest. If we just don't do the variable selection, if we just allow each and every decision tree to be more or less the same, that's bagging. We create multiple data sets. Each data set, we will pass it to a cart algorithm. Each cart algorithm will try to produce a tree, and you are combining them. That's only bagging. But in case of random forest, we add one more twist to it. That twist is, hey, don't just blindly go with this learning process. You try to filter variables. You randomly select p variables out of the m variables at every split level. Okay, so that way, we will bring more democracy into the trees. And what this helps us is to reduce the probability of overfitting. One or two trees can overfit, but by doing this randomization process in the variable selection, we are giving more freedom to each tree. Even if one or two trees are overfitting, other trees compensate for them. So to make sure that all the variable combinations are perfectly used, we in case of random forest, we actually go with a very high number of trees, sometimes even 100, sometimes even 500. It depends upon the number of observations you have. Probably if you have 1,000 observations, we might go to 20, 25. But if you have lakhs of observations, sometimes we even build 500 trees. Computationally very expensive, I have to admit that. So imagine building one single tree has to go through so many processes behind the scenes. First, it has to find out the split points in each variable. Then it has to find out the best split point in each variable. Then it has to repeat that process with each variable and compare these splits that across each variable to decide which variable to make the split at one node. If so many calculations has to happen to decide at one node, imagine the number of calculations it has to complete if it has to train one model. Now you are saying repeat this process for 500 trees. So it becomes computationally very, very expensive. And that's the reason you need to have very strong infrastructure when you have to perform data science. For these practice examples and all, you don't see that computational complexity because they would not take much time, hardly like 5-10 minutes to complete. But in practicality, when you go to the industry, when you are trying to train models using these ensemble techniques with very large data sets, sometimes the training process go into hours, if not days. I have trained models which took more than 72 hours to get trained, right? So as you go into this complexity, you get used to it. And 72 hours of training on what? Even very powerful machines. From something like 64 core CPU with 512 GB of RAM. Just imagine 64 core CPU and half a terabyte of RAM, and still it takes 72 hours to complete the training. Of course, that's not bagging. It's actually a boosting model which took that much amount of time. But these things become common. These things will become routine for you. Just don't imagine that every problem that we are going to solve is going to be as simple as this. Just run this and in a couple of seconds you would get your results. No, that's not true in data science. Sometimes training models takes days together because of the computational complexity. Why? You can see it here. So many decisions it has to take for one single tree, and it has to take repeat this process for almost like 500 trees. Now, how good your CPU is, how powerful your CPU is, how many multi-threads it can create, how many parallel processes it can run. So it all depends on the infrastructure capability as well a little bit, but at the same time, no matter how good your infrastructure capability is, these computations are time taking. So that's why your model training times will go into number of hours and even number of days. Okay. Let me pause here. There are a few more concepts which we will be discussing, but first let's see an example of this, and then we come back and try to discuss those other concepts, additional concepts, along with the random forest that we have discussed so far. Before that, any questions? I see a couple of them on the Q&A window. Let me answer them first. Yes, there will be a significant difference when we allow repetitions and when we do not allow repetitions, right? So go back to that analogy that I have given you, where 20 chapters divided between 10 people, each person is going to get opportunity to learn only 2 chapters. Now there is a problem. One problem is, what if one of the person doesn't learn? Just for some reason that person doesn't learn. Now what happens to your collective intelligence? It's as good as 9 people. the other person is just a dummy. Now, because there is no repetition, if there is a question that comes from the person who has read those two chapters, that person gives you some random answer, you believe that. So your collective intelligence is going to get dented because of that one particular person. Okay. Same way here, if you do not do repetition, let's say you build 5 models, 4 models are good, 1 model is not good. That model effect will flow into the rest of the 5 models because you are aggregating them. You are trying to summarize them. Okay. Yeah, picking the numbers using the random number generator. I explained the process, how it is done pictorially before. I hope that's clear now. Now let's look at the example of the random forest. Okay. Rest all the steps so far will just remain the same. I'm just going to show you how we train this random forest model. From sklearn.ensemble import random forest classifier. So this feature is called as the autocode filler. So whenever you type a particular word, just a couple of letters and then hit tab, it will show you where the functions that exist with that particular set of characters that we have typed so far. So here I am going to pick random forest classifier. This is a classification problem, so that's why I'm actually picking a classifier. If it's a regression problem, I would pick random forest regressor. Okay. Rest all of the steps is same. Our X train, X test, all are ready. I do not have to recreate them. So as of now, our split of train and test data set is also ready. So I'm just going to use the same split, but going to train them using random forest rather than going with the previously decision tree. Here, one disadvantage is my single decision tree is already doing an amazing job. It has an accuracy of 0.959. Now going with random forest might not make much of a difference, because when you already have a 96% accuracy, what else you would expect, right? So just for the sake of repeating it, we will try to do that. RF is equal to, this is a alias name, the model object we are initializing, and we are trying to give a name to it. It doesn't have to be RF. It can be any valid Python object name. So if you know Python, if you know what are the rules to name objects in Python, you can pick any valid name as an object name over here. But don't just simply think that every time I create something like DT, and these are not any keywords. Those are just the names, and a name can be anything. So we are calling the function random forest classifier, and we are giving the alias RF. Now rf.fit. Okay, you know that each model will have n number of arguments. The main process in training a model is choosing the right values for all of these parameters, right? But which ones to use, which ones not to use, just because of the reason that it is a parameter over here, it doesn't mean that you have to use that parameter and set some value to it. No, most of the parameters will have default values. Criterion is equal to Gini. We will never change that. You know why? Because when we trained a single decision tree, we know Gini index is the splitting criteria that we will try to use, that we will try to minimize. And compared to entropy, Gini is much faster in calculations. And when you are trying to train something like 100 trees, yes, number of estimators is nothing but the number of trees that we are going to build, the number of bags that we are going to create. So here n estimators is equal to 100 by default. So that means if you do not mention how many you want, it would by default choose the number of estimators as 100. If you choose, let's say you start with 25, you start with 30, yeah, it's up to you. So At what number of estimators this model performs very well, we don't know. We will have to iterate it and find it out. So that is where things becomes more and more challenging. Let's say we have to build random forest model. You try to build with 25 trees, someone tries to build with 50 trees, someone else tries with 100 trees. At some point, you get the best set of results. Which one is that set? That's the reason we have to do this process iteratively. We have to train these models iteratively. This part of training process is called as the sorry, I forgot the name. Parameter tuning or hyperparameter tuning. Okay, so we will have to do this hyperparameter tuning in a way we find the best combination of these parameters so that our model does an amazing job, right? Let's start with it, and then we will go ahead and try to do the hyperparameter tuning. But for now, I will start only with one of them, that is called as random underscore state. And why? Even in the random forest, you are trying to create 100 bags. So every time you run this step, those 100 bags will look slightly different. You do not want that to happen. When you create 100 bags, each time you run this code, those 100 bags, whatever the 100 bags that you are going to create should be same. What I mean is, let's say first time observation number 1 went into bag 1, bag 9, bag 10. Next time when you run this code, there is no guarantee that that observation will go again into bag 1, bag 9, and bag 10. It might go into different bags. That will cause some issues. So to repeatedly send the same observation to same bags, we fix this. This is called as the seed for random number generator. So random number generator algorithm has a parameter called seed. That means to produce consistent results, you need to fix this seed, and that's why I'm giving the seed as 1, 2, 3. The magnitude of this number has no meaning. Either you give 0 or you give 1, 2, 3, or you give some number. It's just the same. But to repeatedly produce the same bags, we are giving this seed. So we are only fixing that part now. What we give here, by this time you should be familiar. We give x underscore train, and then we give y underscore train. So that means this is my input, this is my target. You try to learn how to predict this target from this input. That's what we are asking in this statement, rf.fit. Oh, it ran pretty fast. Even for 100 trees, it didn't take much time. So that's a good sign. So the model is not going to take much time in trying to learn. Now let's do the same routine job of prediction. First, we will do train prediction. We will print the train report. So this is the train report. I'm going to just copy paste this code here. Okay. Train report 0.9677. That's the training accuracy. It looks okay. Okay, fine. Wait a minute. We did not run this. Oh, this is the problem. rf.predict. So RF is the random forest model. DT is the decision tree model. So that's why this one did not change. I was surprised both random forest. Now let's see the training accuracy. Training accuracy is 1. It can happen, right? Even the decision tree, when we did not control the tree, it has happened. But I will be more hopeful that random forest test accuracy would be slightly better compared to the decision tree accuracy. So this is going to be the test accuracy of the random forest model, rf.predict on next test, and then you print the confusion matrix. 0.973. Look at the model performance of the single decision tree test report 0.959, close to 0.96. With no fuss, our random forest was able to beat it. So that's why ensemble techniques are very, very powerful compared to your single decision trees, which has its their own weaknesses when they are actually learning from some large set of data. Ensemble techniques doesn't have those weaknesses. They are weak learners, but combined together, their combined intelligence would any day beat the intelligence of a single model, single decision tree in this case. Okay. Now let's talk about this parameter tuning. We started with number of trees n underscore estimators, right? So let's see what those estimators are. 100. As of now, number of estimators is equal to 100. So let's say we change that to 25. Let's start with 25. Let's see how, as we change the number of estimators, what is going to happen to our training and test accuracy. So as you repeat this process many times, you would know what is happening to your model as you change your number of estimators. So this is a very good way to learn how these models work. Play with only one parameter at a time. Of course, there are other parameters. We will go with the other parameters, but for now, let's start with number of estimators is equal to 25. Let's run this entire process. Oh, decreased a little bit, 0.996 compared to 100. When I decrease it to 25, 0.996. That's not a big deal. That's not a big decrease. Even here it decreased a little bit, 0.967. That's still okay for me. I would not bother much about 0.971 to 0.967. Now let's change this to 50. This one to 50. And let's try to retrain the model. .999. Okay, pretty close. Oops. Maybe I use the wrong keys on the keyboard. This is called as a code block in Jupyter Lab or Jupyter Notebook. When you change this code block to something like Markdown, this becomes non-executable. It's like a comment, right? So that's why I'm going back and trying to change this to a code block. Now the test report, 0.968. Previously it was 0.97. Now it's pretty close, so 0.968. Maybe I'll stop here and say, hey, no need to even train up to 100 trees. 50 trees are definitely doing a decent job for us. So we would stick to this 50. So like this, you look at how many parameters we have. You need to understand these parameters one by one, and you need to practice in such a way that what these parameters does to your model slowly, again, one by one. You can still see max depth. Hey, what's max depth? Max depth is a limitation on the decision tree, how far the tree can grow. But why do we have max depth here? This is random forest, right? Even now, each tree can overfit. Some of the trees can grow pretty long, leading to overfitting. So you might want to restrict all the trees. It's like a blanket restriction. So let me add a blanket restriction. Max depth is equal to 7 now. Previously, when there is no such restriction, some of the trees might have grown all the way to, let's say, a depth of 10, depth of 12, or even some depth of 11. But right now, I'm restricting all the trees to grow only up to a depth of maximum depth of 11. So my training report 0.999, not much changed, and my test report 0.952 decreased a little bit. Though the training did not decrease much, but my test has decreased a little bit. Now let's say we increase this max depth to 8. Let's see how this one again impacts our model. Let's run the test report again. 0.961. Okay, in this case, 8 is better than 7. So max depth, we might go up to 8, right? So we have to do n number of iterations, so many combinations. Due to the time restriction, I would not be able to explain each and every parameter here, the importance of each and every parameter here, but I will talk about a couple of them, just only a couple of them. As you learn more about random forest, as you try to practice more with random forest, you would have to slowly learn about each of these parameters, what this particular parameter does to your model, how do you control or how do you get the maximum out of the model of this model by controlling these parameters, right? As I said, I'll talk only about a couple of them. Let's choose those couple of them. One of them is minimum samples in leaf. This is another parameter which is quite handy. So what is minimum samples in leaf? Let's try to understand this from a single tree perspective. How does a tree grow? What's happening? Starting from the root node, we will just keep splitting the data as long as we reach the leaf node. Let's say this is the leaf node. And we are giving minimum samples in leaf node is equal to 1. So minimum underscore samples underscore leaf underscore node. By default, it is set to 1. Now we will change this to 10. What happens is when the split is attempted, we are trying to make this split. This leaf node ended up with 6 observations. What is the condition? Early stopping criteria, like maximum depth, which is one early stopping criteria. Another early stopping criteria is minimum samples in leaf node is equal to 10. So here, when we allow this split to happen, let's say we got 6 here, we got 12 here. This is becoming a leaf node, but here we have less than 10 observations. So that means this split is not allowed. It would stop here, 12 plus 6, 18 observations. So this becomes our leaf node. So these two will get eliminated. These 2 leaf nodes are not acceptable at all. Okay, so that's the criteria this minimum samples underscore leaf does. So we should have at least these many observations in the leaf node to accept it as a leaf node. If it has less than that, now I have changed that to 10. If it has less than that, then this will not be acceptable as a leaf node. So what happens is the previous node itself becomes a leaf node. So all these early additional stopping criteria are introduced, are included just to make sure that none of the trees get overfitted. Sometimes even after including max depth, not all of them, when you grow hundreds of trees, even after having a restriction on max depth, some trees can overfit. So to control those overfittings across all the trees, these are some of the parameters. These are some of the options that we use. So that's one important parameter apart from max depth. Another parameter apart from max depth is this one, max underscore features. You remember that random forest also does variable selection, variable sampling. At each split, you would not allow all the variables to compete. You would only allow a sample of variables to compete. And what did the rule say? The rule says if we are performing regression, then if the total number of parameters is m, then for regression it will be m by 3. The number of parameters that will compete p is equal to m by 3. If we are performing classification, then we have a rule which says p is equal to root over m. Let's say if your m is equal to 20, root over m is equal to 4 point something. So we would only allow 5 features or 4 features to compete at each split level. If you are performing classification, if you are performing regression, then it is 20 by 6. So we would allow up 6 features to compete at each split level. So here we have to make a split. If we are performing regression, we would allow 6. That's like x1, x3, x9, x14, x6, something like this. If we are performing classification, then we will allow for x1, x3, x9, x11, something like this. Okay. When you give max features is equal to auto, auto means use these rules to select the number of features that you are going to sample. For regression m by 3, for classification root over m. That's what auto means. Instead of leaving that option to random forest algorithm, you can decide it. You can say, hey, don't worry about these rules. Select 4, select 5, or select 6. You can decide how many variables are going to compete at each split level. So that's like you have to ask explicitly, you have to pass random forest algorithm, hey, just only try these many variables at each split. Make a competition between these many variables at each split, right? So finding out the best values for all of this is the competition that you are, is the main job that we have to do as a data scientist. And this is what we call as the parameter optimization or parameter tuning. Why anybody can build a random forest model if this is like 4 lines of code, 5 lines of code. Where it makes a lot of difference is having knowledge about all of these parameters, knowing what each of these parameters does to your model, picking the right values for these parameters so you get the best out of random forest model is the main goal of a data scientist in building the model. After building the model, we still have a lot of things to do, but in building the model, even before you say, hey, I have built a model which is making decent amount of prediction, you have to ensure that you have find out the best values, the best combinations for all these parameters that gives you very good predictions on your test data set. One more last caution that I would like to add is this one. N underscore jobs is equal to none. This parameter has nothing to do with model training, but it can decide how fast your algorithm is going to learn. This is the parallelization parameter. So if you have a 4-core CPU, the quad-core CPU, generally most of our personal computers would be 4-core CPUs. Some of the latest ones will have 8 cores, i9 and all. I'm not sure if any one of you has a 8-core CPU, right? So when you give n underscore jobs is equal to none, it will probably choose the number of cores it has to use for computation by itself. But if you specifically mention like n underscore jobs is equal to 4, then it will use all the 4 cores available in your CPU for execution. Be a little cautious with this. Why? Because if you say n underscore jobs is equal to 4 and you have only 4 cores in your machine, it will throttle your CPU to 100% usage. And your computer, as long as this model is getting trained, is completely used by this particular random forest training itself. So you do not have any CPU left out for other tasks, right? This is a common mistake a lot of people does without knowing. They just keep trying some numbers for each of these parameters. That's not a good sign. If you do not understand a parameter, better to leave the parameter to default value instead of randomly trying some values. Don't think that each parameter can take any values arbitrarily. It will not. There are some restrictions. So in this case, you have a restriction based on your CPU. If you have a 4-core CPU, at the max you can give n underscore jobs as 4. If you give beyond that, it would throw an error. Like you do not have physical infrastructure more than 4. It cannot run more than 4 threads for you, right? So that's why be a little more knowledgeable about each parameter before you try to use them in training the model. Okay, so far so good. Let's pause here, see if there are any questions. Yes, some of the people asked about the data set and this code yesterday. Yeah, I will share all of them at once. tomorrow is the last day for this workshop, right? So I'll zip all of these as one single file and I'll share it with all of you. Yeah, minimum samples in leaf is what we have discussed so far. Minimum samples in leaf means when the, let me again do this again. So to start with, we have this root node, and then we keep splitting this. We get child nodes, we get these child nodes, and let's say we are trying to split this child node again. There are 18 observations here, n is equal to 18. I'm trying to split this using some condition, x3 less than p. 6 observations came on the left hand side. So left hand side child has 6 observations and the right hand side child has 12 observations. Now if I put restriction saying minimum samples in leaf is equal to 10. This is the early stopping criteria that we have set. These two are supposed to be leaf nodes. Supposed to be leaf nodes. But if these two become leaf nodes, this condition, early stopping condition, is not satisfied. This one only has 6 observations. Though this one has 12 observations, right side child is fine, but this one will only have 6 observations, and that's not acceptable as per this rule. Minimum samples in leaf is equal to 10. So this is not acceptable at all. What we do, we will not allow this split. So this split is eliminated. So this becomes our leaf node. If we allow this split, these were supposed to be our leaf nodes, but we did not allow this split because of this extra condition. Now it has actually stopped here. And because of this, this becomes our new leaf node with 18 observations. So whatever is the majority here, whenever observation ends up in this node, we will give the prediction based on the majority in this node itself. We would not use these leaf nodes. We would restrict the tree to this itself. I hope that's clear now. Okay. There are a lot more concepts to be added. Don't simply think that whatever we have discussed so far is good enough to build a random forest model. If that's simple, everybody would be able to build a random forest model by now. It's not that simple, right? As I said, the more and more complex topics that we have to combine. For example, the validation that I mentioned a little while ago, validation is another very, very important topic we would have to learn. Just to give you a brief about it, what validation means is, so far, when I try to build a model, we split the data into train and test. Generally, train 80% and test is going to be 20%. No, that's not acceptable in the real world. We would not do that. We would go with another additional process, like this is my train, this is my validation, and this is my test data set. So validation and train are used during the training process. So when we train a model, when we are trying to do the parameter tuning, we would not use the test data set for the parameter tuning. We would only use the validation data set for the parameter tuning. Make sure that your model performs well on the validation data set. Once it's done, once it's final that your model is doing a pretty good job on the validation data set as well as the training data set, then we will bring in the test into the concept. Until then, we would not test the data set. So this is a 3-level approach: train, validation, and test. And sometimes we would not have this leverage of a validation data set. Why? Already our data set is too small, 80% data going to train, 20% data going to test. So this 80% becomes so small. And once we make another split out of it called as validation data set, our training data set becomes even smaller. We will, smaller the training data set, tougher the learning is going to be. So we want bigger data sets to actually learn from. So what we do is bring in one more additional concept called as like cross validation. So you can learn about this cross validation concept on your own. So you can use this cross validation concept along with the random forest in the parameter tuning. So as we go deeper into the data science, the complexity of these topics will keep increasing to make more to make sure that the model that we are producing is the best out of all possible cases. We need to add all these additional ingredients into your modeling, right? We bring validation. If validation is not possible, we bring cross validation. So all of these topics combined, you would definitely get the best model as an output. So that's where you have to learn. Make a note of all these concepts and try to search about these concepts. Most of these concepts are straightforward. You should be able to learn about these concepts on your own. Just that it would be slightly tricky when you try to combine this concept with whatever the concepts that we have learned so far. With a couple of examples, you should be able to easily do that, right? Okay, now let's see if there are any additional questions on these two topics, be it the yesterday's decision tree or today's random forest. Tomorrow we will freshly start with our new topic called as boosting. Now we have today more time for questions. Feel free. A few people are raising hand. Unfortunately, I don't be able to have a vocal discussion. You could post more questions on the chat window. That would be more helpful. Does random forest overfit? Not really. It's well known that random forest model doesn't overfit that easily. It might overfit when you go with too many number of estimators. Like if you try to build 1,000 estimators. Just to give you a perspective, let's do this. To start with, your training data set has 2,500 observations. And we are building 100 bags, right? When you are building 100 things, we are building 100 bags. If you equally divide them into each bag, how many you will get in each bag? 25. 25 is too less, we would not. So what we would do, we would allow repetition. Let's say each bag has 250 observations, 250, 250. Now, instead of 100, this is like 100 bags. Instead of 100, we go with 1,000 bags. What happens? Each bag, if you try to randomly divide them into 1,000, each bag will get 2.5 observations. That's way too less, right? So if you repeat 250, 250 now, what happens? There will be a lot of duplication in the bags. Some of the bags would be exactly same. This bag and this bag would be exactly same. And that's the reason why having too many trees would probably lead to overfitting. And that's the reason we need to find out what is the ideal parameter value, number of estimators. Start with something low and keep increasing it. And that's the reason I iterated with 25, then I went to 50. At 50 itself, I have got a very decent score. So I don't even have to go up to 100. So if you go with a very high value for this number of estimators, there is a possibility that you would probably making a random forest model to overfit as well. Why? Each tree becomes same and the decisions made by these trees are same, and these three decisions will dominate the decision making, and that's the reason why you would be probably getting to overfit. But when you go with a smaller value and slowly increase them, you would probably not have this problem of overfitting. So starting with a smaller value of number of estimators and then slowly increasing would avoid that overfitting problem. I do not have a YouTube channel of my own, but if I start, I would definitely communicate. there is a catch here. Will it work if all the variables are categorical? Yeah, so that's a fantastic question. Now, when you have categorical, this is part of feature engineering. If there is a concept, if in future in one of the tutorials, I will definitely take the basic concepts more. I will take feature engineering as one of the concepts. In feature engineering, we have two types of feature engineering. For example, if you have a categorical variable, let's say the variable name is variable 1, it has values A, B, C, D. And since these are non-numerical ones, dealing with them is slightly tricky. What we generally do is we create dummy variables called variable A, variable underscore B, variable underscore C, variable underscore D. So this is called the concept of creating dummy variables or one-hot encoding. If we all are categorical variables and we do one-hot encoding, these models will not perform very well. They will struggle. Why it will struggle? In place of one variable, we are creating 4. If variable has 10 levels, we would create 10 variables. That's like diluting the data. It doesn't make much of a sense. Then your model will suffer. So more of a algorithm problem, it should be a feature engineering problem. The way you try to deal with your data, that's going to change. So we will talk about these things in feature engineering, not model specific. So in the life cycle of data science, first is your data collection part. Second is your data cleaning. Third one is your feature engineering. Fourth one is model building. So what we are discussing here is the model building piece, not the previous ones. Okay. Instead of one-hot encoding, we have something called as categorical encoding. There is another name, label encoding. Either we call it as categorical encoding or label encoding. So we can try label encoding. So in the order of importance, parameters, first parameter that you would play with is number of estimators, because that's the one which is going to impact how big or how smaller your bags are going to be. That would impact how good each model is going to learn from. So that's why I said this is the most important parameter. Next in the list is your max depth and minimum samples in leaf. Next in the list is max features. So that's why I only highlighted those features. I did not highlight the rest of the features. The reason why I highlighted those features in a chronological order is those are the important parameters, and exactly in that order. Okay. Yeah, label encoding means replacing A with 1, B with 2, C with 3, D with 4. That's exactly what you are talking about in label encoding. It has its own merits and demerits as well. So you need to consider what type of algorithm you are using, and for that algorithm, can you use label encoding or not? That's some decision making that you have to do. But alternate for one-hot encoding is the label encoding. Keep posting your questions if you have. So how to choose the right metric for algorithms? That's part of basic data science discussion. What kind of model that you are, what kind of problem you are trying to solve. Regression, for regression, the metrics that we use is RMSE, mean absolute error, mean absolute percentage error, MSE. So there's a whole bunch of metrics that depends on each problem. For classification, it will be accuracy, FN score, precision, recall, and a few more, AUC, right? So if you need more of them, you just look at the introduction to data science. I think I discussed most of these metrics in that. Not always increasing a parameter means increasing the accuracy. No, sometimes it could be like counterproductive. Let's say in this case, if I change the number of estimators to 1,000, model will overfit and it would decrease the performance, right? So you go in a order to make sure at what level you get best. Anything beyond that is leading you to decrease the accuracy, right? So not every parameter increasing the accuracy means it will increasing the parameter value means it will increase the accuracy. Don't believe that. Don't believe like that. Hmm? For classification, it is precision, recall, and FN score. Those are the best metrics that we use in case of classification. Tomorrow, if I have more time, I will explain what these metrics are: precision, recall, and FN score, because they are slightly confusing and it would take a lot of time. That's why I did not introduce them in this session. Possible, if there is time, I will talk about those three metrics. Okay, I hope that was informative. If you continue on learning more and more about it, it becomes more fruitful. This is just, as I said, as a high level introduction. Train and test accuracy, we are building a model and you use the model to predict the values of the training observations again. It's like learning from the textbook and just trying to make sure how good learning is again on the textbook examples. That's your training accuracy. Test accuracy is you go and take new examples that's slightly similar to what you have seen in the textbook and trying to do that on the textbook examples. Trying to do that on a different examples than the textbook. That's called your test accuracy. It's like train score and then the test score. If these two are good, then you mean it's a good job, right? So your learning is good. It's not depend on what type of problem, what type of examples you are looking at. You are scoring good both on it. Okay. Yeah, a lot of people are asking for a YouTube channel or something. I don't have one right now, but if I start, I will definitely communicate. Both should be equal or close to each other. Closer the better. Both should be equal. Equal is never a possibility, very rare, right? Let's say you get a training accuracy of 0.95, you get a test accuracy of 0.92. That's good. There is not much difference between those two. But training accuracy of 0.95, test accuracy of 0.8 is not acceptable because there is a huge difference. That means you have trained a model which is learning too much from your training data, performing well on the training data, but not on the test data. That's overfitting. Okay, looks like we don't have any more questions. Training can be 100, but testing is training 100 is a rare case. I said this is a play data set. The reason I choose this one is because it trains very fast. In a workshop like this, if I run something which is taking 4 hours to train, that doesn't look good. So that's the reason I took that small data set. But training 100 percentage is never a possibility in the world of data science. It's very difficult. Yeah, that depends on the data set. If your data set is like that, yeah, your training can become 100 percentage. In practicality, no.
Yes, Sagar sir. Sir, thank you very much for the nice session.
Okay, sir.
Sir, thank you, sir. Sir, can I close the section?
Yeah, okay, sir. No more
Yeah.
questions coming.
Thank you. All the participants, please fill the feedback